recyclable and cannot be recycled after curing. On the other hand, thermoplastic resins can be recycled. In Europe, plans are in place to ban wind blade in landfilling altogether by 2025, which is accelerating the development of recycling technologies for blades. One of the most common thermoplastic resin for the recyclable blades is Helium-188, which was developed by Arkema in France. Helium-188 can obtain a high-performance composites product through a standard manufacturing process, offering all of the benefits of thermoplastic polymers. Helium-188 is a recyclable thermoplastic resin, especially used for manufacturing wind turbine blades. In fact, the world's largest 100% recyclable prototype wind turbine blade made of Helium-188. However, in this study, we'd like to perform the studies to further investigate the thermoplastic PMMA-based resin system. In fact, there are many research on recyclable resins, which is based on MMA as a monomer. Initially, studies on the MMA polymerization process were mainly conducted. At this stage, basic studies on the polymerization conditions and reaction mechanism of methyl methacrylates were conducted. After that, PMMA, which is polymerization methyl methacrylase, is applied in the composite area. Helium was developed in around 2015, and it applied to structures such as wind turbine blades to provide higher durability and environmental sustainability. Again, in this study, we would like to perform the studies to further investigate the thermoplastic PMMA-based resin system. Now, let me introduce the key responses of resin needed for wind turbine blades. The first one is induction time. Induction time refers to the time after adding an initiator in MMA and before radical polymerization starts. As MMA polymerizes, the temperature rises rapidly. As the temperature rises, viscosity increases as well. So from this point on, the infusion process cannot be carried out. Therefore, induction time is really important because it has to be in time for the infusion process. Next one is strength. It affects on blade durability and performance. Last but not least is viscosity. It determines the speed of infusion. If viscosity got too high, then the resin would be cured in the middle of the infusion. On the other hand, if viscosity got too low, then resin would be not reached until the last laminate and just flew away. If the viscosity of the resin is adequate, then it would be well infused and cure well. In general, methyl methacrylate needs accelerator and initiator system. We can control the ratio of them and adjust the strength and induction time. But we need the proper viscosity too, so we can adjust the viscosity by combining this ratio and PMMA powder. However, we could get a worse value than the previous one. Therefore, it is necessary to consider synchronizing the factors of PMMA accelerator and initiator to control viscosity, strength, and induction time. However, this method is really inefficient to test and conform all of them because there are so many cases. DOE, design of experiments, is based on to analyze multiple factors simultaneously and minimize the number of experiments. Design of experiments is a statistical methodology that systematically design and analyze the experiments to identify key factors, reduce variability, and improve quality. It promotes efficiency and cost savings, supports the optimization of products and processes, contribute to implements of quality management programs, and enhance the reproducibility and robustness of experiments. First, we need to make a sampling. There is a response of interest obtained in the form data after experiment. So we need some experiment data to make a sampling. In the experiment, we have some factors that influence results. That's a design variable. We can construct a meta model with that experiment value. We can construct the approximate model and get an expected value that we haven't experienced. Then, the optimal value can be found in the constructed meta model. The process is called design optimization, which is find to expected optimal value through the analytical model. We can perform real experiments using the expected optimal factors and compare them to the expected results. If the results are good, then all of this process have gone well. Now I'll introduce one example that I used for optimizing resin system. First, I made a sample of experiments that I conducted before. In here, I used initiator and accelerator to attribute value. Responses were tensile strength and induction time. After sampling, I made a meta model using Piano, which is optimal design program developed in Korea. This is very effective in conducting optimal design using DOE methodology. Using this meta model, it is possible to obtain expected value for points that have not been tested based on existing experiments points. And also, we can identify the correlation between each attribute value and responses. Using previous meta model, we can perform design optimization. In optimizing process, we need to define variables. In this example, it would be initiator and accelerator. And then we set objectives and constraints. Objective choose a functional combination of variables to maximize or minimize, and constraints express combination of variables that must be satisfied by acceptable design alternatives as equations or inequalities. By doing all of these settings, we can get the expected optimal value that satisfies the condition. There is an initial value that I conducted before, and the optimal value is here. Then we can test the experiment value for validation. So I proceed to continue real optimization by adding multiple value and multiple responses, including viscosity and etc. Using the DOE PMMA, glass fiber and UD panels are prepared through the infusion process. We conducted the tensile test and fatigue test to compare mechanical properties of UD composites. Compared to the ilium, the static strength of the DOE PMMA is about 10% higher than the ilium composites, and the fatigue life data were also well matched. And also, we conducted composite compressive test too. Similarly, the DOE PMMA well matched within the ilium. After UD composite test, we conducted the infusion of the full-scale blade in the real industry company with the collaboration with our partner, Human Composites in Korea. This is the whole process of the full-scale infusion. This shows the entire infusion process of 16-meter long blades. Again, the infusion process of PMMA is exactly as the same regular epoxy system. This is a big advantage. We can draw the flow line in the infusion system. After the full-scale infusion, we also conducted the spark gap infusion and performed 3-point bending test using UTM and compared between the DOE MMA and epoxy spark gap. As a result of the experiment, the bending results were measured similar to what we predicted. This is the process of 3-point bending. Compared to the existing epoxy system, it was confirmed that the mechanical properties of the DOE PMMA are very similar. So here is the main conclusion. DOE method enables to find the optimal point with minimal experiments. The optimized MMA-based thermoplastic resin maintained its mechanical properties compared to the conventional thermosetting resin. The new thermoplastic is competitive compared to the Ilium. Thank you for your attention.
Thank you for the excellent report.